Okay, class, welcome to lecture 21. So today we're talking about composition of functions. So composition is a fancy word, but the big idea behind all this is that we now have these things called functions we can study, and composition is just a cool way to take two functions, hip new way, to take two functions and create a new one. And the idea is pretty good because all it is realizing that a function is really just like this way to go from one set to another. So here's just like a little picture of a function from a set with 3 elements to a set with another 3 elements, where I haven't labeled anything. But so this is a function. And then realizing like, hey, if I have another function that goes from the end of the first one to a different function, then I can sort of glue them together. And this makes a function from the first set to the last set by sort of just doing both together, one after the other. So that defines a new function. So functions, we should be able to do one after the other. We should do one and then another. As long as the middle, this sort of set in the middle here, is the end of f and the beginning of g, then it makes sense to be able to do this. Okay, so that's the idea behind composition. But now, of course, the idea is never good enough. We have to have the full real definition. So I need 3 sets. I'm just going to call them non-empty sets just to ensure that they have elements. I don't have to worry about weird stuff happening. So non-empty sets. And then we need 2 functions that we're going to stick together. So one will go from A to B, and the next will start at B where the other one ended and go to the other set C. So these are both functions. Now we're going to define how to sort of glue them together, stick them together to make a new function. And it has a fancy name. So the composition of f and g, that's the thing we're defining here, is a function you get by doing this process. So is the function. So here's its name. So remember how function notation works. We stick the name, I'm going to leave it blank for now, to the left of the colon, and then we say what it goes from and to. Well, the idea is what is this function doing? It's just doing f, and then after that it's doing g. And so that means that this function better start at A, then it goes to B because of f, but then after that it goes to C because of g. So we're doing this whole process all in one go. This is sort of like A, B, and C. So it goes all the way from A to C. Now, what is it called? That's what the name is. So this is a bit of a confusing thing. So which function comes first, f or g? Well, f, right? So you might think I'll put f first on the left because I read from left to right. But you'd be wrong, unfortunately, because math people like to overcomplicate things. So this function is called g, and then a circle, f. And this is called the composition of f and g. And what we do is we write g first on the left, even though it comes after. And we'll see why in a second. It sort of makes sense to do that. But at the same time, it also doesn't make sense to do that. So this is just the name of the function. Actually, I don't need those parentheses there, sorry. So you always put the name of the function to the left of the colon. That's what it's going to be called. But what is it? How do I define it? So to define a function, you have to say the rule. So remember, we write the rule, we can write it a couple different ways, but usually we write it underneath the name of the function. And what we can do is we could say, what does it do to elements of x? Sorry, elements of a. So what should happen when I plug in an element of a? So I haven't said what it is yet. Well, let's think about this little mini example. What does the whole process do? Well, it just does f first. Then whatever that goes to, g is applied to that. And it does that for every single element that you start with. So how can I notate that? Well, first I do f of x, whatever that is, whatever f tells me to do. Then I plug that in g. And so that's why it's written from left to right, because this is a more familiar notation of plugging things into other things. So this says plug x into f, then plug that, all of that into g. That's what this process is saying here. This is like my little x here. Plug it into f, that makes it go over here. Now plug that into g, and that gets me over to the end. Let me label, oops. Sorry, that says f of x. Let me say it better. So this dot would be if this was x to start. Okay. So again, when we write functions, we always write the name of the function of the variable that we're using to say what it does. So on the left here, this is just sort of naming the function and saying what I'm plugging in. This is actually what the function does. So this is really the definition of how to create the composition. So then we can also call it g of f is sort of how you say it, g compose f. It's also called, you could say the whole thing at once, it's called the composite function. I should say also. So there's many ways to see it. You can say the composite function, the composite of f and g. But the whole point is all it's doing is it's doing f and then it's doing g after that. So let's see a little example here. So we need some sets. So I got to make some sets up. So let's see, 1, 2, 3. That'll be A. B will be about Z and Y. And C will be about A and B. Now notice, it doesn't have to be the same letters A, B, and C. And I can put X in one of these, and maybe that would be confusing because I'm using X here to stand for just any old element in the first set. But I avoided that for now. Okay. So let's define, I'm just going to speed it up, I'm going to just draw the functions because it's just a lot faster. So f is going to go from A to B, and then g goes from B to C, so I'm going to label it like this. So you can sort of see it's like a little chain, and B has to be in the middle, otherwise you wouldn't be able to create the chain. Okay, so then in A we have 1, 2, and 3, in B we have Z and Y, and in A and C we have A and B. So I'll just make up a function. So 1 is going to get sent to Z, 2 will get sent to Y, and 3 will get sent to Y. By F, that's what F does. And then G will send Z to B and Y to A. Okay, so I have F in my G, so now I should be able to make G compose F, or the composite of F and G, however you want to say it. And what does it go from and to? Well, it starts at A and it goes through B, but what matters is it gets to C. So you just put the first and the last, the domain and the codomain, right? That's what you indicate when you use function notation, the beginning and the end, the domain and the codomain. And to say what a function does, you have to say what it does to the elements of the first set. So I got to say where 1 goes. I got to say, whoops, where 2 goes. And I got to say where 3 goes to create, to actually say the definition of the function. Okay, well, according to this thing, this is the actual way to do it. So this is saying I'm just supposed to do g of whatever 1 goes to. So I'd look up and I say, where does 1 go to? Oh, it goes to z. So that means g of f of 1 is actually g of z. And then I say, where does z go to? Oh, it goes to b. So really, g of f, that's the name of the function, and I'm just saying where 1 is sent to, and it's sent to b. So that's really telling me what g of f does. You could also use this other notation, 1 goes to b. The little arrow with the line at the end of it. Okay, so then the other ones, where does 2 go? Well, 2 goes to y first, and then y goes to a. So this guy sends 2 where? It sends it to a. And lastly, this guy, well, first f sends 3 to y, and then y goes to a. So, whoops, g of f of 3 goes to a. So then really what's going on is when we create this new function, the middle, we're sort of just forgetting about the middle completely. And so now we're just saying, I have this brand new function that goes all the way from a to c, and this is what it does. It sends 1 to b, and 2 and 3 both go to a. That's what this function does. But secretly, it came from doing this process where you do one and then the other. But then it is its own function from a to c as well. So you can just designate it by writing that. Okay, so that's the idea behind composites. And the big picture is just think about it as gluing two functions together to make a new function. So now, just for some minor little things that can happen. So no, in this case, I could try to do something else. I could say like, oh, what if I do f compose g instead? So what would that mean? That would mean do g first, then do f. But in this situation, it doesn't make sense. So whenever you compose, you have to make sure that it makes sense. Why doesn't it make sense? Well, because this is saying that first use g, which goes from b to c, then use f. But f doesn't come out of c, so it doesn't make sense to do that. You can't do that. So in order to define composition, for a composite to exist, you need the beginning of one to match the end of the other, aka the domain of one to match the codomain of the other. So, for example, if I just had two functions, I'm not going to define them this time. If f goes from a to b, and g goes from z to a, then now what I've been writing, g compose f, doesn't exist, because this is saying first go from a to b through f, then go from Z to A. That doesn't make sense, because how do I get from there to there to do the whole thing? So that doesn't exist. But now, instead, F compose G does exist, because now I go from Z to A, and then from A to B. So that one is defined, or definable. If you have the functions, you can define it. Because first you're going from Z to A, then you're going to B by doing F then G. Sorry, G then F this time. Because that's what they were up there, right? Yeah. Okay, so just a little stuff to be aware of. So the nice situations are when you just have one set to deal with. And that's what happened like in like your calculus classes, sort of pre-calc, is you're pretty much always just working with real numbers. And all your functions are going from real numbers to other real numbers. So in that situation, you could just sort of compose whatever you wanted with whatever else you wanted, and without having to worry too much. So let's think about what happens when you can do both directions, where you could do F compose G and G compose F at the same time. Okay, so just to practice, use the other notation. So here's a function you're familiar with. It creates a parabola. So F takes x to x squared. And G is also going to go from the real numbers to the real numbers. And I'll send x to, I don't know, how about x plus 1. So now both things make sense. F can be composed with G in this order, where G comes first, because I'm going from the real numbers to the real numbers to the real numbers. So I begin and end in the same place. And this one, I go from the real numbers to the real numbers to the real numbers. These both exist. So let's just see how they're related and how to figure them out. So now in this situation, my functions are defined by saying what I do to an element using variables, instead of literally saying like up here, which each element goes to element by element. And so how does this work with composition? Well, you actually have seen this before probably, and it's not so bad. So then, okay, which one should we do first? Let's just do this one first. Okay, so how do I define this? So it's supposed to, so to define a function, I have to say where the variable x goes when I'm using sets that consist of numbers, and I define my functions in terms of where the operations that the variable goes through, like squaring and adding and stuff. So I can just say what x becomes. Well, what I know is that the way that composite works is you're supposed to do f of x first, and then you're supposed to g that. So all I have to do is say, what does f turn x into? That's this. And that's also what this is. This is just saying, what does f turn x into? It turns it into x squared. Now, what does g turn x into? It turns it into x plus 1. But now my x is x squared. So what's it going to turn x squared into? Well, x squared plus 1. It just takes whatever you have and adds 1. So to define a composite where you're using variables, all you have to do is say where the variable goes from the first function, that's what's happening here. Then you have to say where the next function takes that new whole thing. Okay, so that's going to be g of f of x. So what about f of g of x? So I'm just interchanging notation using equal signs or using arrows, just so you get used to both. So, oops, f of g, this function, that's the name. Where does it send x? That's how I define a function like this. Well, it sends it to, first you do g of x, then you do f of that. So where does g send it? sends it to x plus 1. Then where does f send whatever you plug in there? Sends it to that thing squared. So notice, not the same. So what that means is that the two functions, these two processes, are not the same function. Now, we didn't talk about what it means for two functions to be equal, but it's sort of exactly what it should be. Two functions are equal, so I'll use different names like, I don't know, h and k. Two functions are equal if they're equal on all of their elements that you plug in. And what we've shown here is that this does not happen. In fact, it would rarely happen because the equations are so different. If you plugged in 0, that's like one of the few times where they would be equal. But to be equal means that they have to always be equal on every single element that you plug in. So in general, these two are not the same, even when you can compose both. Sometimes you can't even make both of them, you can only make one. Okay, so that's an interesting fact, that the order matters in which way you compose. You get two different answers depending on what you do. Okay, so that's going to be it for example stuff. Now we're going to do the big stuff. We're going to do proofs. And the way we're going to do it is we're going to combine the idea of composition with stuff we learned last time with injective functions, and surjective and bijective. So just to remind you before we jump into that, injective functions basically look like this, where everything goes over because it's a function, but no two things go to the same place. And surjective means that you just cover up everything in the codomain, even if you overlap or something, it's fine. And then surjective or bijective is when both happen. Okay, so what's interesting to think about is when you combine injective functions using composition or surjective functions and thinking about what are the possibilities that could happen. And we can sort of think about it already. If I have two injective functions, one after another, then it should stay injective because nothing is getting squished down by either of them. And same thing should happen with surjective functions. If I have another one here, it's going to continue squishing everything down and covering the entire thing. Whereas if I have another injective function, the composition should stay injective because in both cases I'm not squishing anything down. Okay, so that's the idea. Now let's do the proof. This is a very good example of a next level proof. So I'll say what that means in a bit. Okay, so here's the idea. We have two functions. And we just want to see what happens if we compose injective functions and surjective functions. Here it is. So if f and g are both injective, then when I create the composite, oops, that's going to also be injective. Same thing for surjectivity. If f and g are surjective, then this guy is also surjective. And then same for bijective. But remember how to prove something is bijective, you just prove both of the first two. So if I prove the first two facts, then the third fact comes true too. Okay, so let's do these proofs. These are wonderful proofs. A lot of fun. Okay, so it's an if then, right? So my if is that these two things are both injective, and I'm trying to show this guy is injective. So let's rewrite that down. So F and G are, oops, they go between different things, so I can't just comma them right there. So F has to go to from A to B. G will go from B to C. B injective. So remember what this means. I'll just do some scratch work over here. So when is a function injective? So F injective means, remember, it's an if then. If the outputs are equal, then the inputs are secretly also equal afterwards. And this happens for any two inputs that you can pair, any two inputs in the whole world. So why is this a next level proof? So this is a next level proof because we have to assume a definition that's in the form of an if then. So what that means is in the proof, because we know F is injective, how do we actually get to use that in the proof? Well, people get very confused in this type of situation. If you know F is injective, and this goes for any if then definition, that means that when the if part occurs in your proof somewhere, you get to conclude, because that did happen, the hypothesis is met, that this happens. So that's how you actually use a definition that is assumed. So in the proof, because we know F is injective, when you see F of some, it doesn't have to literally be x1 and x2, it could be something else, but if you see something of this form, you can conclude x1 equals x2. So this is sort of a next level of ability in terms of being able to prove things, is being able to use definitions like this. Okay, so that's what it means for F to be injective. G is also injective, so you'll get to use the same fact. So when you see this happening, you get to conclude x1 equals x2. But again, what's actually inside of the functions could just be, you don't know what they're going to be yet. You don't know what these will be. But you'll know that if you see f of something equals f of something, that you'll be able to do this. And same down here. The variables names are just placeholders. The point is, if you have something that is injective, then if this occurs, you get to conclude this. But you don't know how this will occur in the proof. You don't know where it'll show up until you get there. Okay, so that's some good scratch work. So the difference here is that when we did like stuff with rational numbers, after you said, okay, x is a rational number, then you're going to immediately write what you can say about it. But what I can say about f and g is nothing until this shows up. I can't use this information until this shows up somehow. So I'm not going to expand upon f being injective in my proof at all, or g being injective. I am going to refer to the scratch work later, but repeating the fact that it's injective in the proof is not going to help me, because I'm not going to be able to do anything with it like I would with like a rational number or a definition where you get to immediately say something about the thing you just wrote down. Okay, instead, we're just going to jump to what I want to show. Show this guy is injective. Because I know how to show things are injective, I know that I get to assume something. What do I have to assume to show something is injective? Well, I got to show this definition, but it's not f, it's g of f. And that means I have to assume the if part and show the then part. So injective proofs always work the same. When you're trying to show something is injective, you consider two elements, whatever you want to call them, in the domain. You assume that they get sent to the same place by the function. What's the function this time? It's g of f. So you assume that these are equal, that they get sent to the same place by the function, and then you show that the inputs, the domain elements were actually the same the whole time. Okay? So now that I've assumed something that has an equation in it, I can go somewhere. Assuming that these are injective, again, I'm going to keep being very repetitive, I can't say anything yet because I have to be in a situation where I see this to conclude this, or down with G, same thing. Okay, but here I've actually assumed an equation, so I can just expand upon that equation to continue. So how do I expand upon it? Well, what are these things? Let's just write these out. What is g of f of x1? Well, that's just the function g of f plugging x1 in. But what is that defined to be? That's just g of f of x1. But then I could do the same thing with this one. So g of f of x2. These guys are equal. That was assumed. So now I'm really focusing on the fact that these are equal. So let me just rewrite those separately just to keep it nice and clean. So now I know this. And now this is where your expertise, once you get used to it, comes into play for looking at your assumptions and using them. So now I have g of something equals g of something. So this is where I use the definition of g being injective. Since g is injective, so notice I didn't to use the fact that g was injective, I did not like make this happen. I didn't like set this equal or something. It just happened because of what I was trying to show, this. So that's how these kinds of definitions will work in the proofs when they are assumed. You don't get to create this, whoops, you don't get to like force this situation to happen. It just happens. You get to conclude something once it happens. Since G is injective, I can now say that the inputs are equal because the outputs are already equal. So this means f of x1 equals f of x2. Because that's what it means for G to be injective. When you have equality of outputs for any two things you plug in, then you get to say that the inputs are equal. Okay, but now I'm in the situation where I have f of something equals f of something, and I know f is injective. So since f is injective, I'm going to do the same thing. Since f is injective, and I have f of something equal to f of something, I get to automatically conclude that x1 equals x2. So notice, again, I did not set these equal. I did not set these equal. What I set equal were these things, these two. I did this because I was trying to show that something was injective. And then naturally, this just happens. And then I got to use that G was injective because it happened. Same thing here. This just happened. I didn't set them equal. They just were equal because of something else. And then I got to conclude that the insides were equal. But now we're done. This shows G of F is injective because what does it mean to be injective? It means plug into elements of the domain, set them equal, show the insides are equal. That's what I wanted to show. I did. So we're done. Okay, very good proof. I would highly recommend practicing that one again. Number 2, if F and G are surjective, then their composite is surjective. So now we're going to let them be surjective instead. It's going to work very similarly. So I got these two functions. They're both surjective. Same idea. Let me remind you what it means to be surjective. It just means that no matter what you have in the codomain, you can find a way, you can plug something in. Oops. You can plug something in from the domain that gets you that element of the codomain, that output. There's always a way to find, there's always a way to get to any output. But because this is being assumed, it's different than when I'm trying to show something is surjective. If I'm assuming it's surjective, what that means is that because this happens for any y in the codomain, if I see something in the codomain, if you see something in the codomain, you get to conclude, you get to use that to say that there exists this element in the domain. But I guess I'll call it y, see something, see y in the, but it might not necessarily be y. It could just, it's just if you see anything in the codomain, because it's surjective, you're able to find this thing in the domain that gets sent to it. You're not trying to show that, so you're not gonna let something happen, it's just gonna happen. And then you're gonna conclude something. Same idea for how you use definitions that you have assumed instead of the ones that you're trying to show. G is also surjective. So same idea. So if you if you have something in C, but it's not going to be called Y, it could be, you don't know what it'll be called, you just have to have something in there. What you can do, you can conclude that there's something, same idea, that gets sent to it. Okay, so keep that scratchbook in mind as we go through the proof. When you assume something, that means you get to conclude something if you see something, versus when you're trying to prove something, you let something happen and try to make the other thing happen. Okay, so now these are surjective. I want to show G compose F from A to C is surjective. So how do I show something is surjective? I have to find something in A for everything in C. So I gotta let something be in C. I'm gonna call it Z, doesn't really matter what you call it, to show that this guy is injective. I have to find something in A such that when I plug it in to my function, it takes me to that Z. That's how you show something is surjective. You let something be in the codomain, find what gets sent to it. Okay, so again, what can I do? Well, all I know is that I have this element in C. Aha, but what else do I know? I know G is already surjective. So what did we say over here? If you know that the function is surjective and you happen to have something in the codomain, then you get to do something, you get to conclude something. Because it's already surjective, you can find an element in B getting sent to it. So I guess I won't call it X because I already used the letter X, I'll call it Y. There exists a Y in B such that F of Y equals Z. Sorry, G. Cool. So now I have this Y, and where does it live? It lives in B. Oh, but F is surjective. So that means if I have something in B, I can find something in A that goes to it. So that's the next step. So since we know something is in the codomain, now there exists something in the domain of that function that's already surjective, which is f, that if I plug it in, I get y. So I really want to plug something in to get to z, and I want to plug it into g of f. Well, now we have that thing actually. Have I found something in A that if I plug it in to g of f, I'll get z? The z that I assumed existed, that I let happen? Yes. Because what is this thing? Well, it's just g of f of x by the definition of the composite, but f of x is really y, and g of y is really z. So I've done what I wanted to show. I found an element that gets sent to z. So I accomplished this. Okay, so that means it's surjective. And so part 3 is just true because of the previous two. So if f and g are both bijective, then the composite is bijective. That has to be true too because the first two, because if they're both bijective, they're both injective, and that means the composite is injective. If they're both bijective, they're both surjective, so that means the composite is surjective, so that means the composite is both injective and surjective, so it is bijective. Okay, so you can write that proof out if you want, or ask me for help. If you can't do it, let me know. Okay, so we're moving on to the next theorem. Slightly different, sort of more interesting. I think that the theorem we just did is sort of, it makes sense that it should happen. The composite of injective is injective and surjective is surjective. This one is maybe a bit more fancy and tricky. Okay, but it sort of works the same. So if I have two functions, we get this sort of more strange result. If the composite is already injective, so this is weirder because first I'm saying something about the composite, then I'm going to talk about its components, its pieces. So if that's already injective, then, well, it doesn't make them both be injective, but it does make F be injective, which is sort of interesting. So let's draw a little picture first. So this is saying that if going, so there's like my secret B in the middle, A, B, C. So this is saying like if I go all the way over here and I'm injective, so nothing gets squished down, that means that F had to be injective in the first place. But G actually didn't have to be injective. So G could have been surjective, and I think I see how, because I could have sent these other guys, I could have squished them down, because they didn't come from anything in F. So I think that's going to be the idea. If you want an example of how this works, then make functions that look like this picture. Okay, so let's do the proof though. So there will be a second part, but I'll just do this one first. Let this composite be injective. Show F is injective. So again, because I'm assuming that this guy is injective, I'm not going to conclude anything now about anything, but I am going to use that fact in this proof somehow when it pops up. Okay, so I'm just going to start what I need to show instead. Show F is injective. So how do I do that? I let two things be in its domain, which is A, and I assume that they both get sent to the same place. Then I got to show they were secretly the same all along. So in an injective proof, what I get to use is this. But I don't have actual functions. This is very general. I don't have a specific formula to use or anything. So that means that this proof requires a trick because I can't immediately go anywhere. So here's the trick. Plug both sides into G. And this trick takes some experience to see. I can see it because I've done it a million times, but it does take experience to see it the first time. If I plug both sides into G, why is this good? Because then I'll be able to use information about G of F that I have, which is that it's injective. So I am going to plug both sides into G. So since f of x1 equals f of x2, when things are equal, I can just do the same thing to both sides. I can use them the same way. So I can certainly plug them into the same function and get the same result. So I'm plugging them both into G, so they should give me the same answer because they're both the same thing. So now I'm just going to sneakily rewrite this using the name of the function. This is what it actually is called, of x1 and of x2. And now, because I know this guy is injective, whenever I see that I have g of f of something equal to g of f of something else, I get to conclude that their inputs are equal. And so I've shown what I wanted to show because of this. I've shown x1 equals x2, starting from f of x1 equals f of x2, so that shows f is injective. So once again, the way it works is if I know something is injective, if it's assumed to already be injective, then the idea is I get to use an if-then, which means if I see the if occur, I can conclude the then. So this is the if part of g of f being injective. If this shows up, then because I already know it's injective, I get to conclude the then part of the definition, which is that their inputs are equal. So that conclusion is just because I couldn't always do this, but because it's already injective. And when I'm trying to show a definition, I'm trying to show how to get from there to there, which is what I've done with F. Very subtle difference. Takes some practice and a lot of practice to get used to. Okay, so the second part of the theorem is sort of the opposite. If this is already surjective, then G will be surjective. So we can just draw a little picture to convince ourselves first for a little bit. So this is saying if you got all the way from over here to over here, and you covered up the whole set, maybe you covered up in multiple ways. Oops. That's fine. If you did that all the way from here to here, that means that G has to be doing that automatically. But F doesn't necessarily have to be doing that. So how could that happen? Well, if you had some extra guys here and here, sorry, no, if you just have extra guys there, you don't need that one. If you have some extra guys in B, then it's got to go somewhere, so it still has to go to C over there. Then you can see that G is surjective, but F doesn't have to be because it doesn't cover up everything over here. It misses that guy. So that's the idea. Okay, so you can create some functions that do those things, that follow those pictures to get more examples. Okay, so now I'm letting the composite be surjective. And I want to show G is surjective. So again, knowing that this is surjective, I don't do anything with it immediately. What I do is I say what I want to show. So what do I want to show? I want to show that no matter what guy I pick in C, I can always find something in its domain, in G's domain, that when I plug it in, it gets me that guy. So all I know right now is I have some Z and C. And immediately now I get to use this guy. Because this is already surjective, and I have something in the codomain, I can use the if-then idea. The if is met, I've found something in the codomain, therefore I can get something in the domain that maps to it. So since this guy is surjective and I already have something in the codomain, there exists something in the domain such that if I plug it in, it takes me to that element. So now I'm really trying to find something in B though. So I need something in B. I have something in A. So this X here was really a placeholder. So maybe I shouldn't use X over here because I don't want to repeat the variable. So let me change this one to something else. I'll call it A. So the trick to this proof, this one also requires a mild trick, is to see, since A is in A, I automatically have a new element in B. Where does F of A live? It's got to live in B because F goes from A to B. And I have something in A, so it takes me to B. So this guy is in B, and what else do I know about it? If I plug it into G, I get Z. That already is true because that's what came from having this little A. So Z equals that thing, but then that thing just equals this thing. So I did find something. G of F of A equals Z. So my F of A, that's the thing in B that I was looking for. I found something in B that maps to Z. So F of A is in B, and G of that thing equals Z. So G is surjected because given something in the codomain, I was able to find something in the domain that maps to it. And that's what it means for G to be surjective. Okay, so that's the end of the lecture. I will see you next time. Hopefully this video wasn't too long.